Right, let's start. Welcome to the graphics programming virtual meetup. And today we will talk about PBRT before starting from the section 3.6, where it's talking about arrays. So array is an origin and direction. So there's two members, origin and direction. And then with a scalar value t, we can get any point on the array. So this is method for that. Each array in PBRT also stores a time value. I don't know what this is for. This is not a common thing. So, but does anyone have insight on this?
I don't know. Maybe just how long the array needs to run for. And give some limit if it doesn't hit something.
It's
within
for
that time.
animated objects. So yeah, I don't know. Maybe later we will know what this is for, but yeah. Also for the participation medium at the origin, I think this is also not a common thing to store in the array, but I guess, yeah, it make other things easier this way, I guess. Mm. It is a constructor. And also ray differentials. Ray differential is a subclass of ray. So everything works for ray differentials, but it has additional information for camera ray offset by 1 samples in the X or Y direction. This is used for the textures. So again, textures will be talked about later in section 10. Oh, a comment says that this time is maybe for motion blur. Yeah, maybe. I forgot how to implement motion blur in a ray tracer, like ray tracing when weekend, or is it second book had the description of that, but I forgot how it was implemented. And bounding boxes, there's also a short section where PBRT has bounding boxes that is used both for AABB, but also just for like any 2D rectangular tiles. So that's why it's a template that supports both integer and float. Its storage is 2 points, the minimum point and the maximum point. And by default, it it just stores empty bounding box by like having the minimum point using the maximum number and maximum point using the minimum number. And also there's a constructor to have a bound with just a single point like this. Or the 2 points ones is more common. This is a helper to get the corner, the one of the 8 corner of the bounding box. And this kind of ridiculous amount of logics operators going on to get this right. And union is a very common operation for bounding box, both union of bounds and points, and also union of the 2 bounds. Intersect, whether 2 boxes overlap with each other, whether a point is inside the box, and also this version just check for a single point. No, check for the exclusive version. So yeah, it's less than or equal, and here is less than. This is useful for integer stuff. For floating point, there are almost no differences. And also some helpers for getting the distance from a point to the bounding box. And also expand the bounding box by a constant factor in all dimensions. Diagonal just gets a vector from the bounding box. Surface area, this is useful. This is really useful thing because a lot of ray tracing stuff needs to do surface area heuristics. So getting the surface area of a bounds is very important. And so volume, I also have, here is this lerp method that linearly interpolate points between the corners of the boxes. That's why its shape doesn't look like a normal lerp, because it uses the corner of the bounding box. And the offset is the inverse of lerp. It returns a continuous position of a point relative to the corner of the box. I think Freya Homo talks about the inverse lerp in one of her articles. I think it's a useful read.
is that like finding the distance between 2 points? Because that's kind of what it's kind of what an inverse lerp would be. Oh, given 2 points and a third value, finding out the inverse from it.
Yeah.
It's basically how much blending should be done.
And also bounding sphere creating from a box. Yeah, this is a far looser fit because especially I think if the box is like not very like each side are not equal lengths, then I feel like it will be a very loose fit. But yeah, I think maybe some operation is easier to do with a sphere than a box. I think for real time, like calling, sometimes people use bounding sphere, but I don't know in ray tracing when this is used.
Yeah, bounding boxes and spheres are always a trade-off of do some small computation to save you a lot of extra computation, like, not rasterizing a triangle or a model if it's behind the camera because the bounding sphere is outside the frustum, but the cost of that, the construction of the bounding volume and the comparison of it has to outweigh the performance loss of, doing something and having it be useless, which
Yeah,
it's always a trade-off. Hi, kitty. Okay, sorry, I shouldn't mute.
and some other helpers. And yeah, the interesting thing is like for integer bounds, they use it for this basically. They use for you can iterate each point inside the integer bound. So this is kind of like their way of writing a nested for loop. I kind of like this.
What
And
did that, sorry, what did that last sentence mean? The iteration goes up but does not visit points equal to the maximum extent of each dimension.
I think
Oh,
it
it
just
doesn't go
means
over.
it's
Okay,
inclusive.
I see. So it
Just
seems like
yeah,
the upper bound is not past the maximum extent.
yeah.
Yeah, okay, got it.
Yeah. I think this kind of makes sense. Just consider how a for loop works. So you normally we write something like for I equal to something and I less than something.
Yep, makes sense.
Yeah, and this is a long chapter about spherical geometry. So PBRT has a lot of things working with spheres. So first is this concept of solid angles, where we have a planar 2D angle. One way to think about it is as a projection to a unit sphere, and the area on the unit sphere is well, I guess it's not area yet, but the arc length on the unit sphere is the value of the angle. And planar angles are measured by radians. And that's why, like, the whole circle is exactly 2 pi, because it's the length of the whole circle. And solid angle is defined similarly. Solid angle in 3D is a projection onto the unit sphere. And solid angle is measured by steradians. The entire sphere extends for 4 pi, which is the surface area of the sphere, and the hemisphere is 2 pi. That's why, like, in graphics, we often have this divided by 2 pi, divided by 4 pi, this kind of thing, because we want to integrate over a sphere or a hemisphere. Yeah, it mentions we often do some kind of integrating by using the solid angle. Spherical polygon, this is a concept that I am not familiar with, so I just read about it yesterday. The idea is to have some arbitrary polygon in space and then just project it onto a unit sphere. I just feel like I still need to understand this section more. So I guess I will just not bullshitting about what it is, because I still need to read it again myself. But the basic idea is just project a polygon into a unit sphere. Then the third section is about spherical parameterizations, where, because sometimes representing a point in Cartesian coordinates is not the best way to represent a direction. And PBRT has different ways to represent a sphere, but each has different advantages and disadvantages. The first one is the spherical coordinates, which is the very well-known parameterization for the sphere, where we can see the diagram here. Another interesting about spherical coordinates is that, see those two. There's a convention where we have data here and phi here, and there is a convention, we have data here and phi here. So,
Oh,
so
God, I didn't know about this. Why? Why?
just because people like to do this kind of things, we also have like left-hand coordinates, right-hand coordinates. Just whenever there's a chance people can invent arbitrary conventions, people will do to confuse everyone. And usually when people write something, they will not say what kind of convention they use. Anyway, so these PBRT books use the physics convention as mentioned by Wikipedia. So every of those equations are derived from this physics convention in PBRT. And this function convert from spherical coordinates to our Cartesian coordinates. Interestingly, it does not take data as angle, but as sine and cosine to save some costly trig functions. But for phi, it's still just pass phi because as it said that sine and cosine of theta is usually already available in the color, but phi, sine and cosine of phi is not. So it's okay to just compute them on the fly. The conversion of direction to the spherical coordinates can be found by some also probably even more expensive arc and inverse trig functions. But a lot of time we don't need to do trig functions because trig functions are expensive. For example, giving a unit vector omega, then it's easy to compute the cosine of the angle theta by just doing a dot product. And yeah, this is much more efficient than first doing inverse trig and then do the cosine again. Just we are doing repeated work. And I guess this is a kind of thing that can more easily be overlooked when we abstract stuff into functions where we just have a bunch of function calls and then actually one function is doing inverse trig and another function does like trig function again, then we're just doing repeated work for no reason. But yeah, if we have this insight, we can try to avoid it. And yeah, if we have cosine, then for the sine, which we can just use this identity. So sine square is just 1 minus cosine square. And yeah, tangent can be computed by the sine divided by cosine. So by this way, because we compute cosine by the dot product, then nothing, we don't need any standard trig function to calculate those at all. And sine cosine of the phi angle can be found by without using inverse trig functions as well. It's like just again using this formula where cosine of phi is x divided by r, and we know the r on the here is exactly the sine of theta that we already calculated. So, and for sine of phi is similar. And octahedral encoding, this is another way other than the spherical coordinates. So spherical coordinates can compress a point somewhat from 3 float to 2 float. It's not really fit for store unit vector. But of course, Cartesian coordinates is even worse. It uses 12 bytes of memory, and most of the 12 bytes are wasted because a Cartesian coordinate point can represent the arbitrary lengths. If we really just want unit vectors, it doesn't make sense. And spherical coordinates is nicer. It have 2 floats, but also it have expensive trig functions and inverse trig functions to manipulate. Also, yes, spherical coordinates provide more precision near the poles and less near the equators. So we still have the problem of some of bits are wasted, and sometimes we don't have enough precision. And octahedral encoding just solved all this problem. There's a paper on this. If someone can find the link, let me see if I can find the link. No, but yeah. The basic idea of octahedral encoding is we first project from unit sphere to the octahedron like this. And then we flatten the top side and then unfold the bottom side like this. Which result in a whole sphere. Every point on the sphere, we get it into a rectangle. And yeah, for converting a unit vector to octahedron is simple. At first, we need to project a vector from 3D, from the sphere into the octahedron, which can be done by divide by the L1 norm, which L1 norm is just, we add the absolute value of each component. And this is because if we think about it, the L1 norm is exactly the distance between the center to each point on the side of the octahedron. And then for the direction in the lower hemisphere, then we need to do more work because we have this unfold process, but still there's this computation. We can do this computation that don't even have conditionals, even though it's with the help of this sign function that is used the standard copy sign to achieve that. So this is octahedron encoding. To understand this, I highly recommend the paper that I will find the link after we stop the recording. Equal area mapping. This is another thing I never heard before reading this chapter.
I mean, isn't it all about trying to minimize distortion and error during the mapping process? Just for different purposes and different representations have trade-offs.
Yeah. I thought I understand this yesterday, but now I forgot. Oh, sorry about that. No, I don't know what this is anymore. Yeah, but anyway, it's a representation from each point on the sphere to this square. Bounding direction, this is also for culling purpose. So for a light source that emits in some direction but not in others, then we can do some culling. And PBRT provides a direction cone class, which represent a cone. And the comb is represented by a direction and radius. I guess I should not call it radius, it's just an angle. And the angle again is specified by cosine because we don't want to do trig functions on the fly. We can test whether a point is inside the comb or not. If it's not inside, then we can just assumedly do less computation. And also this bound subtended directions function that returns a directional comb that bound a direction subtended by a given bounding box. And here is how the bounding sphere becomes useful, because doing this computation with the box is non-trivial. So we first convert it into a bounding sphere. Then we do computation on the sphere. There's also a union function that just combine two combs to another one. Yeah, I think we will stop at here for this section. I skipped over a lot of details. Some of them because I didn't understand them myself. But others I think it's something you only need to read when you want to actually implement this.